I have a new arcade cabinet. This is a arcade machine micro. I got it from AliExpress. It is terrible, so let's open it up and see how it works. So I had previously seen these on AliExpress, but had always ignored them as I thought they were just more NES clones. If you're used to them, you will know and loathe that music. But that is not what this is. This is based on a completely different architecture that does not involve ripping off old Nintendo games. Before we get stuck in, let me give you a brief tour. It comes in an unbranded cardboard box, as all these things do, although surprisingly enough, this one does actually have a sticker on the side with the manufacturer on it, about which I have been unable to find any information. Inside the box is an instruction leaflet that is boringly poorly translated, so I'm not going to bother looking at that. There's very little information on the box itself, so we might as well go on to the machine proper. It's surprisingly well made. There's a battery compartment on the back that takes 3 AAAs, a decent switch. It's surprisingly solid. The controls on the front are not entirely terrible. We've got 2 command buttons, a mini joystick, and a few rubber function keys. And this 1.8-inch LCD. And it's this LCD that seems to mark these devices. The magic phrase for finding these on AliExpress is 1.8 arcade. So let me fire it up and give you a quick tour of the games. Now, the first thing you will notice is that this thing has an FM synthesis engine. It's got a lot of MIDI music, and after a while it all sounds the same. Sadly, this is coming through on the microphone at just the right volume, so I don't really have an excuse to turn it off. But anyway, the main menu has got lots of pages of names with bizarre names like Where to Go and Flying Bullet and Catch Chicken and Color Stone and Link. They're all very low effort jobs that are clearly written for this thing. So let's just pick something at random. Twin Shot. How does this work? I haven't played this one before. You seem to be able to fire arrows. It's a basic platformer. Here is Bear versus Bald. Where you are a bear. And there seem to be shoes, maybe cars. I think this is a Mario Brothers clone, the original one, not the Super. This is Raiden. Which is a generic shoot 'em up. The joystick is not brilliant, but it does function, unlike my game playing skills. This is Honey Mary. Apache Overkill. Snowball. Eating Worms with 2 T's. So it took me a while to figure this one out. Your character can only move in straight lines until it's stopped by something, which is a fairly traditional puzzle game. But we also have the ability to swap with the red thing, which in turn blocks your space, which is how you get hold of like this item. Again, I'm sure this is a clone of something, but I don't know what it is. This is one of the less terrible games. Boldly Egg, which is one of these. There is only one button, which is the jump button. Shoot penguins. You will never guess what this is from the name. Sky War. That's some good royalty-free MIDI music there. Star Battle. Another vertically scrolling shoot 'em up of no particular interest. Mars Mission. Destroy Hubble. NS Shaft. Aeronaval War. Anyway, enough of that because the noise is doing my head in. It's actually quite loud in real life. Inside there is not a lot. We've got a real speaker. We have a cheap and nasty PCB with a hair in it, which I shall remove. Which is attached to the LCD, and there is a daughter board here with the controls on it. And now I see that the screws that hold the daughter board on are facing in a direction where you can't actually get them off. This bit just pulls out, and then I bet that this bit comes off as well. Excellent. So now we have the joystick unit, which, as I thought, are just some of these mushy silicone switches, which explains the unique key feel. And under the LCD is the works. And the works consist of a single blob, which contains the CPU, the RAM, the LCD controller, you know, the usual stuff, and this. And full transparency, I did actually know this was here before I took it apart. This is a serial EEPROM, and this has got all the games on it. Let's take a closer look at this PCB. We have two black wires for the speaker here. This comes from the battery compartment, but there's also some pinholes here for powering it. Here we have the serial EEPROM with the games on it, but there's also another serial EEPROM footprint over here. I don't know what that would be. This is where the controller pins thing plugged in. That all looks suspiciously hand soldered, as does this. I don't really like the idea of somebody wasting their life soldering these things together. Here's the clock crystal, which is external. This is surprising. Other similar devices I've seen just use something internal to the blob. And these are just blocks of foam to maintain the proper separation between the PCB and the LCD which sits on top. The great thing about serial EEPROMs, of course, is if you remove them from the board, they're really easy to read. So let's remove it from the board. Not my best work, but it should function. So we're now ready to read it. This is not the correct chip ID, but it is one that works. This seems to be a 4 megabyte chip. So we now have a file. It is 4 megabytes. And what do we see when we look inside it? Okay, so this is good news. Some of these devices tend to encrypt what's on the chip badly, but it's still really annoying to decipher. But this all being the same looks relatively simple, but there is something slightly odd about what we're seeing. There's a lot of E4s. It could be that all the data is XORed with a single byte, probably E4. So let's run it through strings and see what comes out. Garbage. Okay, I think it is XORed. So XOR search is a handy tool which searches the binary file for a given known good string and tries to figure out any instances where that string occurs XORed with a particular byte. We know that the string score appears, and there we are. And yes, it's all XORed with E4, which is nice. However, I can't find a turnkey tool for undoing the XORing, but they're trivial to write. So here is one. I've compiled it. So all I need to do is this. XOR image. And when we look at it, we see this. So all those E4s have turned into zeros. And we should be able to find our score string here. Okay, what's this? Oh, these are the names of all the games. Okay, so it looks like we've successfully decoded the ROM. So now we have access to the actual contents of the ROM. Let's try and find out what it is. This is CPUREC, which is a tool for guessing what CPU architecture a given file is. It uses heuristics to look for various known patterns that appear in different types of machine code. So let's find our file and fire it off and see what comes out. And we have an answer, but it's not a very good answer. It says it's found a small chunk here that looks like 6502 code, but it doesn't have anything for the whole thing. So I should come clean here. A while back, I did this same exercise with a VTech toy laptop, and to my complete astonishment, it turned out that the blob chip contained a 6502 processor. Now, one of the things about SPI flash chips, they act basically as files. They have an internal seek pointer. You seek to a particular address in the flash, and then you can read or write bytes. What you can't do is map them directly to a CPU bus. But this VTech laptop was doing exactly that. What it was doing was that the internal CPU had its bus mapped to a protocol converter. So every time the CPU read a byte from memory, it would generate an SPI transaction to seek to the relevant place on the flash chip and read a byte. This is hideously inefficient, but given the 602 is very slow and SPI chips are very fast, it worked. And because this thing has its games on flash, it must be doing something similar. And I was hoping this would be another 6002. but it looks like CPU rec doesn't necessarily think so. Okay, let's take a look at this ourselves. There is only one thing to do now, which is to fire up my favorite reverse engineering tool. Okay, I've imported just the raw image into Ghidra, and CPU rec said it found something at A800. So let's go to A800 to there and tell it to disassemble. Yep, this is C602 code. This is valid 602 code. So all the addresses are wrong because I don't know how the memory map of this thing works. But this looks like a 602. I mean, this is doing sensible things. Loads A with the register, does a comparison, then does a branch based on the result of the comparison. If carry is set, jump to here, add with carry the value in here. It hasn't reset the carry because the carry is known to be clear because of the BCS here. Yeah, this all makes sense. This is a 602. That's amazing. So what do we get? The beginning of the flash? Nothing. This is clearly gibberish. Gibberish. Okay, now, I bet this is the same blob chip that the VTech thing was using. This is a clone 602 by Sun Plus or General Plus. As far as I can tell, this is from doing research when I was doing the VTech thing. But I bet this works exactly the same way. The blob will have a mask ROM internally containing a big library of 602 code, stuff that does stuff. And this is mapped directly to the CPU bus. So it is way faster than the external SPI stuff. And this internal ROM handles all the graphics drawing commands, sprites, sound handling, and so on. So the fact that the SPI is relatively slow is unimportant. Okay, I'm going back to my VTech project and figuring out how the ROM works, and we'll see if this works the same way. Unfortunately, that would be a no. The structure of this thing's ROM is quite different from the VTech Toys ROM, which contains these data blocks at the beginning of the ROM and a jump table down at 8800 to various entry points that the built-in operating system calls. This clearly works very differently. It's probably got a different payload in the mask ROM. If you buy enough from the manufacturer, they will let you specify your own payload. And I'm sure they have various standardized payloads for, cheap and nasty toys like this arcade machine. So at this point, I can either attempt to reverse engineer the code from what I've figured out here, or, and this is my preferred approach, go back to the hardware and see what it's doing. Here we have the logic analyzer hooked up. It's connected to the flash chip's I/O pins. It will log everything that happens to the flash chip. So all we need to do is start it running, turn the thing on, and we'll have a record of every memory access the CPU does to the flash chip, including when, where, and the value that's being read. From there, we should be able to figure out what this device's boot up code is, and hopefully get a handle on where to start reverse engineering the code. So this is what I ended up with. This is the entire signal. You can see the timeline up here. This is about 10 seconds of data. I turned the thing on around here. It woke up and started doing stuff a couple of seconds later. Here is where I turned it off. And as all the capacitors drain and the voltage drops, we get random gibberish until it finally trails to a halt and I actually stop the capture. The bit we're interested in is this section here. You can see quite clearly that there is a little burst of traffic here, another little burst of traffic here, and then lots of stuff going on here. And I think that this is the operating system starting up. This is it doing something else, I don't know what, but this is probably it playing the music for the title screen off the flash chip. Now, it took me ages to figure out what was going on here because I was looking for signals in the 248 megahertz range. In fact, this thing talks to the flash chip at 24 megahertz, which is ridiculous for a device like this. I bet the CPU itself isn't running nearly that quick. But here in the initialization code, you can see most of this is details of the SPI transfer. But this line is useful because this shows the actual commands being sent. So, read from address 9, and then it reads back 6 bytes. Here's another read from address F, 6 bytes, etc. And this line down here, which just shows individual commands. We can see it reading chunks of data from bits around the top of the ROM until we reach this section where it reads 318 bytes from the flash chip. And you can see the address, which is 18F6. If I go over to Ghidra and disassemble from 18F6, this is indeed 65C02 machine code. So this is clearly some kind of startup code. However, here there is a JSR instruction. Now, if this was actually executing the code as it read it, then when it hit the JSR, we would be able to see it stop the current read transaction and open a new one from the address being jumped to. Or if it was jumping to a subroutine in the internal ROM, we would see a gap as it stopped reading bytes from flash. So what I think it's doing is it's copied all this into a buffer for execution, which makes sense for startup code. Later on, we have a big gap, which is probably the internal ROM doing something. And then there's another piece of code. This is at 1F41. So we can go there and disassemble. So disassemble, there we go. And this is interesting. These are clearly hardware registers because you can see it loading values and then writing them to the same address consecutively. If this wasn't a hardware register, this would be pointless. So this is clearly doing some kind of hardware setup. And then here we return back to the caller. And here it's doing something from 18F6, which is in fact the thing we just looked at, which is interesting. Okay, let's take a look at the main chunk of the code. If this was executing from flash, as I said, I would expect to see fairly short transactions. So here is one starting at AC1. What's this? This is machine code. Okay, that's not calling anything, so that's not helping us. Here is 6 bytes at OB. Now, I can tell immediately that this is not machine code because that OO on the front is a break instruction. Or it could be machine code and they're doing something really weird with break instructions. The break instruction on the 6502 is a kind of system call. But this one at 7E4 does look more machine code-ish. Yes, that is machine code. Here it is jumping to somewhere. In fact, I've just remembered that the bytes I'm seeing here are not the bytes that the CPU is dealing with because of the XOR. So that 0 is not a break instruction. What is it? 1B. E4. That's plausible, but not very. Like, why would you do a comparison, then immediately store, and don't think that's a valid instruction. So yeah, I think this is data. And I see here the string Tony. I bet that is a magic number of some kind. Here we go, 2231. What's here? That looks like machine code. It is machine code. 59 bytes. So we go to 231 plus 59. So in fact, it's read all the way to here. Wait, I think this might be using hex. So 59 is 3B in hex. Okay, yeah. So that has read just enough for this routine, and a single byte following, which makes sense for the 6502. When the 6502 reads instruction, it always reads 2 bytes. So RTS and the byte following. So that makes sense for a on-demand read. Okay, I'm going to have to go away and pick away at this and see what I come up with. I found something. Okay, 18F6, that's startup code. I think this is loaded into a buffer and then executed there. Here is a JSR instruction. This is calling 042A. Now, it just so happens that if we assume that this is loaded at address 0300, then 042A ends up being this piece of code here, which is immediately after a jump instruction. So there is no way that execution can get here unless you explicitly call it. This is all in the chunk of data that's downloaded. So I'm pretty sure that this is all loaded at address 300, which makes sense. Now, it does occur to me that it might not be being loaded into a buffer. There might be some kind of read cache. So it's just started executing code from here. The SPI bridge goes away and reads a big chunk of data into the cache, and it executes from there. So 0300 may not actually be RAM, it may be memory mapped, memory allocated to the SPI bridge, but I think it's a buffer. Unfortunately, Ghidra is not very good, or at least I'm not very good at making Ghidra good at dealing with complex paging. But this does give me enough to be able to actually write code and execute it on this thing. We just need to paste our new code here at 18F6, and it will execute in place of this initialization code. Of course, this is initialization code, which means we won't have access to anything that needs to be initialized, but it's a start. Here's a thing. When it reads that 318 bytes from 18F6, immediately previously, it has read 6 bytes from address 3. What is at address 3? 18F6. This is the address of the chunk of code that is just read into the buffer and executed. So I think that what we're seeing here is some kind of jump table telling it what to do during startup. I'm slowly coming to the opinion that this thing doesn't have an SPI bridge. I think it works entirely by copying chunks of code out of flash into a buffer in RAM, which is interesting. I think in order to get any further, I'm going to have to dump the internal ROM. And in order to do that, I'm going to have to modify this ROM to do the dump for me. So first I'm going to check that it will actually let me modify the code and there aren't like checksums and things. So here is our startup code. I'm just going to swap these first 2 instructions, which we can see here are 6470 and 6471. So if I just change that to 71 and 70, and then write this to the flash, and then I'll see if it works. Good news, it works, although writing 4 megabytes to this little flash chip takes forever. Right then, now I'm faced with a bit of a puzzle. In order to be able to read back the ROM, I need a way to get data off this thing. It was relatively easier on the VTech because of the SPI bridge. I could just read from random addresses and trigger a read transaction on the SPI flash that my logic analyzer could pick up. With this, not quite as easy. I need a GPIO, but I don't know where any of the GPIO registers are. Here's that bit of initialization code spotted earlier, which is doing some deeply magical things. I wonder if it might be programming some sort of coprocessor? Beats me. But it occurs to me that possibly the easiest GPIO to find is the one that controls the transistor that turns the backlight on, because that gets turned on fairly early in the startup sequence and is pretty obvious when it happens. So let's try another logic analyzer capture. So here is a capture where I have added a line for the output of the LED transistor. It gets dropped to 0 when the light goes on and let float high when the light goes off. This is when I turn the machine off. This is when I turn the machine on. And if we zoom in here, see, this is happening immediately after downloading a chunk at 7E4. So what's at 7E4? Well, it's doing something. So it doesn't obviously look like it's touching any hardware registers. I'm used to hardware registers being somewhere up high in memory. But then I spotted this. This is a timing loop. The PHA-PLA wastes some time by doing nothing, and then this happens 15 times. And the only purpose of this is to, pause. And here it's storing FF to 0 page register 0, and here it's reading it back out again. So clearly it's expecting it to have changed. Maybe that is a hardware register. Now there is an easy way to tell whether this routine really is turning the screen on, and that is to replace this jump instruction, which seems to be returning from the routine, with an infinite loop. That means that the routine will execute, and then after executing, it will hang. If the light goes on, it must be something to do with this. If it doesn't go on, it's something else. So let me try that. And the result of the experiment is the light does not go on. That is a problem, because the light is clearly going on after this piece of code, but if this piece of code didn't do it, then I don't have control of the bit of code that makes the light go on. Therefore, I can't figure out how to make the light go on. So this is going to require some lateral thinking. I found something, and this might be the breakthrough I need. Do you remember that list of game names that we saw in the ROM? Well, here it is in Ghidra. You can see here are all the games. Interestingly, there's a couple hundred of them, which is more than the number of games actually on the system. So I'm not sure what's going on there. But just above it, there is this array, each of which contains a pointer to a game name. Now remember that these are not addressers. These are offsets into the flash. So something must be looking one of these things up and then using that to read the name out of the flash. We know that these can't be loaded into memory as part of a code segment, because if so, these would be code pointers, not flash addresses. So if we go over to the signal analyzer dump, and in this window here I have just a list of all the SPI commands, which is easier to deal with, and I search for 2CDE, here indeed is a write transaction. It is reading a byte at 2CDE. Well, it's reading 6 bytes at 2CDE. I think the read transaction minimum size is like 4, 5, or 6 bytes. Immediately before that, it's reading at 2B48. What's at 2B48? It's our array. So what we're doing here, obviously, is this is reading the flash offset of the first name out of the flash. Then it reads the first byte of the string. A little bit later, it reads the second byte of the string, and then the third byte, and so on. This interleaved stuff here, I believe, has got to do with the music player. Why would the code be reading the names of the games? To draw the menu. Is the menu code likely to be in the mask ROM, in the blob? No, it's likely to be on the flash chip, where it's easily customizable. And in fact, just above all this stuff, here it is reading a code segment from a nearby address, which is at 2A24. And if we go look at 2A24, it is in fact immediately above our addresses. And inside this thing, we can see 2B48. So this piece of code here is calculating the index into that array of an entry. The game index is clearly an A. It gets decremented, shifted left by 1. Top bit goes into 85. We then add on the address and call this routine. And this routine is part of the same code segment. And 3e6 sets up a couple of variables and calls this and loads something from here. I think that what we're looking at here is a system call that reads memory out of flash. Now, 8182, 82 is 0, 81 is the, let me look, 2B48, yeah, okay. So 80 is the low byte of the address. The high byte is passed in A, which is written to 81, and 82 is 0. This sounds like a 3-byte flash address. And then it loads the result from 8D. And in fact, here we can see it loading something from 8E. So after the system call is returned, what is in 8D, 8E ends up in 108, 109. So I think this thing actually reads at least 2 bytes, possibly more, but 2 I know, and they get put into 108, 109. 108, 109 is going to be the flash address of the string. And indeed, down here, we can see low byte of the flash address goes into 80, medium byte of the flash address goes into A, and we call 3e6 to load a byte out of flash, check for the string terminator, etc., etc., etc. So yes, I think this is the menu drawing routine, and I think this is the flash reading system call. This is great because it gives me a way to get data out of the system. By calling this, I can trigger reads from anywhere in the flash. I don't care about the result. What I do care about is that I can see those reads in the logic analyzer. So by varying the address at which the read happens, I get to transmit bytes from the device through the logic analyzer, where I can extract them and put together data. So I think I can now write a program that will dump not necessarily the entire ROM, but at least some of it. So let's try that. Here's my test program. It's very simple. We initialize the flash address at 80. We dereference it. That is, we read a byte out of the CPU's address space. We stash that in the high byte of the 3-byte flash address, and we call the routine to actually read the flash. Then we increment the address, only the bottom 2 bytes of the address, and go around again. So this should dump the entire 64K of address space over and over again. It's been assembled to go into hex 300. So all I need to do now is to patch this into the ROM in one of the code segments that I know will be executed, execute it, and capture the result. And it has worked like a charm. Here's the trace. Here's the code segment that we're loading, the one that I've hijacked. And here is a read. Bottom 4 bytes are 0, 0, 0, 0, 0, 0, 0, 1, 0002, and the top byte is the data. So yes, I should be able to extract everything I need from there. There's also another fun thing I can do. Because I wrote the code that's actually doing the loop, I know how many cycles that takes. So this is the chip select line. This gets lowered when it's actually doing something with the flash chip. It gets released high when it's not. So by measuring how long it's spending not working on the flash in our loop, which is 6.75 microseconds, and then counting the number of cycles in this loop, we should get an estimate of the clock speed. So how many cycles is this? I'm not going to bother actually looking it up for real. This is going to be deeply approximate. I don't know what the read flash subroutine is doing inside and how much overhead there is. So 1 cycle to read the instruction, 1 to read the 0-page address parameter, another 2 to actually do the dereference. Let's call that 4, 3. I think this is 5 or 6 to make the call, and another 5 or 6 to do the RTS. Let's call this 17 so far, 20, 23 to actually do the jump, and another 26 to do this jump. So 26 cycles. Call that a round number of 25. So let me just do the maths. That's about 3.7 megahertz, so I'm going to guess this thing is running at 4 megahertz, which is not brilliantly fast, but is way faster than most 6402 computers back in the day. Okay, I'm going to get stuck in and try and actually decode this trace. So here is the ROM loaded into Ghidra, and I think I'm beginning to get a handle as to how this thing works. I don't think this is using paging, so it's clearly a different part than the one on the VTech. Or, possibly by a different manufacturer. I have no idea who made this thing. I can't imagine there are very many people making 602s these days. But everything from 6000 up seems to be the ROM. You get RAM from 0 to 800, which is 2K. However, the bottom 128 bytes seem to be I/O peripherals. Someone has clearly been looking at the 8051. If I follow the reset vector, I can find the startup code, and most importantly, I can find where it's fetching the encryption key from flash. And it's really, really stupid. It reads a 6-byte block from address 9, which is what we found from the logs here. That's this one. It then performs this calculation on the bytes in the block to produce a single byte encryption key. I'm using the word encryption loosely here, which is XORed with all the data. It then checks this. This is what the next few writes are for. It looks for the encryption key again, except this time encrypted in 2 other places in the flash, and also looks for a checksum, which is just done by adding up all the bytes in the key, which is not how you do checksums. Then it checks for the Tony magic number, and then we actually start executing code. And the way it does code is really weird. Your code is divided into chunks, each of which is referred to by a descriptor. The descriptor contains the position in the flash of the code and how long it is. Over here, I've got, this is the raw flash in Ghidra. Here, for example, at address 3 in the flash, there is a descriptor for that startup routine at 18F6. It's got the address and the length, which confusingly is in words, not bytes. There are then ROM functions that will let you either jump to one of these or call one of these, and it's got a stack that's 6 deep of loaded routines. When one routine returns, the operating system then reloads the previous routine. This all goes into the same RAM buffer at 0300. So you can have as much code as you like in the 4 megabyte ROM, provided each individual routine is small enough to fit within your RAM buffer, and provided that you're willing to take the hit of loading it all from flash every time you do a call or a return. For example, that startup routine took 1.5 milliseconds to load. And there's no buffering, so every time you call the routine, it will take 1.5 milliseconds. And if you call another routine from within this and return to it, it takes 1.5 milliseconds. On the other hand, for what they're doing here, it's probably a reasonable design choice. It means that you can write each game as a single chunk of code, and it will seamlessly page them in and out from flash as you need them. Unfortunately, this will make actually finding the code on the flash a bit tricky, because many of the descriptors are actually in line with the code. Over here is our startup routine. Ignore the symbol names, they're all wrong. But this is the subroutine that calls a child chunk. I'm going to have to come up with names for these things because they're not really the same as functions. Remember that you can have as much code as you like within a single, let's call it a chunk, which means you can have your own subroutines inside the chunk. Those are fast. They're all executed from internal RAM. But here, where we are loading all these values and storing them into these addresses, that is actually setting up a call to the routine in flash address 1D7E, which is E too long. And I should be able to go there, 1D7E. Yeah. here is a routine which does weird things with what I assume are hardware registers. So it'll do all of this, hit the RTS, and then it'll swap back in the previous chunk at 18F6 and continue. So I think I now have enough of the structure to be able to write my own ROMs, although as I have no idea what the I/O is, I can't do anything with them, so there's not really much point. But more usefully, I think I should be able to decrypt the original ROM by simply zeroing out the key and have it still work just as it did before. Maybe. I am making the wild assumption that it's not doing anything else with the encryption keys, which could be wrong. Here it is, 1 byte of encryption key. I can see it's written in 2 places. Here is where the encryption key is actually read, and here is where the computed encryption key is written. But these cross-references only show up for code that Ghidra has actually seen. One decrypted ROM functioning perfectly. I wrote a program here which analyzes the ROM looking for chunks. It finds these based on the characteristic call signatures used to execute a chunk. And because these call signatures also contain the lengths, this allows it to pull out and disassemble all several thousand chunks in the ROM. It's not perfect, it doesn't know anything about indirect calls, but it does allow me to get a good idea of what's in the ROM. It also builds a call graph, which is here. And this is showing a number of rather interesting things. Firstly, our routine which draws on the screen is here. This suggests that this cluster here has got to do with the main menu. If I zoom out, it's very wide. You can see that it's divided into fairly discrete clusters. Presumably one is called by another via indirect calls, which is why it hasn't been able to actually turn it into a full graph. This is a pretty chunky thing, which clearly shares some code here. But anyway, looking at this seems to be the main menu. Now, my routine is capable of distinguishing between jumps to another chunk and calls to another chunk. So these are calls, these are jumps. And the interesting thing is, this is not in a loop. So if it's iterating through the menu, drawing one line at a time, it's not doing it in a simple way. This led me to take another look at 7E4 here, which actually turns out to be the routine I looked at, which may or may not turn the screen on. And if I look at the call trace, 7E4, it's actually called over and over again. And if I go back to the ROM, here is the startup code. So here it's doing the stuff with the flash, etc., etc. Here is our first chunk call. No, sorry, that's the second chunk call. The first chunk call is indirect via this. It could actually use this same routine here, but for some reason it doesn't. It just does the same thing. But this is doing an indirect call and then doing a chunk jump, but it is calling chunk jump as a subroutine, which means that when the chunk finishes executing and does an RTS, it will return here. And then it does something else, and it's in a big loop. So I think that this operating system is event-driven. I think that the first call, the one up here, is the initialization code. And the second call, the one down here through 1B in the flash, is the event handler. And I think it does some stuff, then it returns, and then this does something, and then it shuffles some bits and goes round again. This is actually kind of annoying because it makes it rather harder to reverse engineer. If it wasn't event-driven, then I'd be able to see it reading and writing from all the various I/O ports. But I think everything is being handled by the operating system and is indirect. This is puzzling. This is a extended 6502 instruction. The 6502 has been extended multiple times. Firstly, the 65C02 has got useful stuff like STZ and PHX and PHY, but there's also a few other extensions, and this chip, whatever it is, seems to have adopted all the 6502 extensions. This is branch if bit reset. It looks for bit 7 in this 0 page location, and if it's not set, it jumps to this address, which is here. So it will continuously spin on this instruction until it sees bit 7 set. And then the next instruction here will reset it, RMB, reset bit. What puzzles me is that this is, I think, RAM, not an I/O port. And as far as I can tell, this thing does not use interrupts. If I go find the interrupt vectors here, they both point to the same place, which is an RTI. So either it's not using interrupts, or it's using interrupts of a kind that's not like normal 6502 interrupts. This is clearly gating each run through the event loop. It waits for the bit to be set before it executes the event loop code, and then down here, this stuff here is a bit complex and I don't have my head around it, but here it is, again, waiting for it to be set, resetting it afterwards, and then it loops. So it does this 3 times before changing another bit and going back to the top of the event loop. I do not know why. Maybe it's a timer of some description? I found a vector table, exactly where I thought it would be, just below the old-fashioned 6002 vectors. There are a number of interrupt handlers, much to my relief. If this thing didn't have interrupt handlers, I would be very confused, including this behemoth here. Gidra's not done a very good job of decompiling it, but anyway, one of the things it does is set our mysterious top bit of 9.3. I also found a few other things, including the fact that the ROM is only 8K long. The rest of the address space is just mirrors of the ROM, so it is in fact wasting over half the address space. Not just that, but everything above about 2K, between 2K and the bottom of the ROM at 6000 hex, is also mirrors of the ROM. So this thing's got 2K of RAM and 8K of ROM and nothing else. Anyway, along the way, I found a lot of fiddling with memory location 0. There's tons of places where it is reading a value that's clearly a copy of it, adjusting it, storing it, and then a bit later, like at the bottom of this function, setting it back again. One of the places it does this is in this read flash routine. I think this is a GPIO port. I think what this is doing is lowering the chip select line, performing the flash operation, and then raising the chip select line later. And I suspect that this is connected to a bunch of things. So I'm going to run an experiment where I write some code that just toggles what might be the chip select line, that would be the bottom bit, as rapidly as possible, run it, look at it in the logic analyzer, and see what comes out. If I'm right, that will be extremely useful. And the results of the experiment are, no, it doesn't work. But the second thing I tried, which was to change this register instead, that did work. And over here, you can see, here is it loading my code, and here it is toggling the chip select line rapidly, which is great news, because now that I have at least one output line, I can do things like put a software UART on it by just bit banging the port and get bytes out. I also have an input route once I figure out where the game controls are mapped. It also allows me to get a bit of a better handle on the clock speed, because I can measure one complete cycle of my loop. I can then count the number of cycles in the loop, multiply one by the other, and I get almost exactly 8 megahertz. That's a pretty fast 6002. However, the other thing that happened was that getting the results of this actually took way longer than I thought, like several days. because I broke it. The very cheap PCB has tracks that are held on by Spit and Sweet Dreams, and the adapter I put on to allow me to plug the flash chip in and out put a bit too much strain and some of the tracks tore. I then proceeded to do quite a lot of microscope soldering surgery to try and fix it, and then I hot glued it together to hold the various solder connections on, and then I transplanted it onto a rather nicer development board, and then I tested it, which was the wrong order, because I then had to spend quite a lot of time cleaning the hot glue off again in order to solder one of the wires onto the right place, etc., etc., etc. But it does now work. It's got a larger speaker, which is possibly not a great idea, and an actual ZIF socket and everything, so that is great. I do, however, have a second one on order. While I was doing that, I also found out a number of interesting things by analysing the Gidro dump. One of these things is that this routine here, 18F6, actually initializes the screen. And if I go and find it, here is the code here. Turns out that all those writes to hex 8000 and hex C1000, if I assume that one of them is writing a LCD control command byte and the other is writing an LCD control data byte, everything works out. So here I can see it resetting the screen. Here it's getting the screen ID. Here it's reading 4 bytes. Here it is examining the screen ID and then calling one of each of these chunks to actually do the rest of the initialization. Here is one of the routines, the one that's actually being called on this device. And here's the one that's being called by this particular board. And as you can see, it's just sending a whole bunch of stuff to the LCD controller. Interestingly, this looks suspiciously auto-generated. It's doing really odd things like writing 0 explicitly twice in a row. Well, not only does it not have to reload A here, but this device actually has a built-in STZ instruction. So I think these are generated at build time from a bunch of tables. Because they're in the flash, they're used once and thrown away, it doesn't really matter how much space they take. Going back to the trace, this is a normal boot up of the actual game. We see this little burst of activity here, then this little burst of activity here, and then the rest of the stuff runs. All of this code here is happening inside this routine. This, at the beginning, is loading 18F6 and running it, and then it's got some whopping great delay loops, which extends all the way to here, and then it calls the secondary function, which takes very little time, and then it reloads 18F6 as it returns back up the stack. And then there's another whopping great delay of most of a second, and then the rest of the code executes. But knowing that this is talking to the LCD also has a few knock-on effects, because I can watch it read stuff out of the LCD registers, and I know what they do because the LCD is documented. So I've been able to figure out where the screen width and height variables are, and this tells me that all of the system calls do things with the screen and the height, therefore they must be drawing onto the screen. That then lets me find routines like this, write pixel, which is in the ROM, which writes a pixel's worth of data to the LCD. There is a color table here containing the 16-bit RGB color values for an 8-bit palette. So if you look up at the code here, write pixel is given an 8-bit pixel value. It then sends the 16 bits worth of color to the screen and continues on. This means that internally, this thing uses 1 byte per pixel data, that is 8 bits per pixel. There's not enough RAM to hold a complete frame buffer in memory, so if you're doing anything even slightly complicated, you have to be able to generate and write a complete scan line at a time. The screen has its own video memory, which you can read and write, but of course, reading it back will be slow. So very likely, the various games are computing a single scan line whenever anything on the line changes and writing it out to the appropriate location. One other fun thing is that even though write pixel here is in ROM, meaning it's hard-coded and can't be changed, up here at the top of the flash at 1.3, there is a descriptor pointing at a routine at 2231, which, if I go and look at it, is here. And this is the routine that sets up the screen to accept video data. So even though the routine to write video data is in the ROM, this routine's in the flash, so that this can be customized easily for any particular screen type. However, the ROM is hardwired to only deal with screens that accept 16-bit data, which is interesting. It also means that whenever a game wants to write a scan line worth of data, it's got to call this thing and load it out of flash, which is a surprising trade-off. Anyway, I think I've got a pretty good handle as to how this thing works now, so I'm going to stop the blow-by-blow commentary. I think I've got enough information to go and do a skeleton SDK for this thing, with the ability to actually create your own ROMs. It won't be very complicated, but I can get data out, and I know where most of the ROM stuff is, and I know where stuff is in memory. But currently, I've been working by just ad hoc patching stuff into binaries, and that's not great. And I need to write down some of the stuff I figured out, and also try and figure out what some of these video routines are. And I think the easiest way to do that is to just call them and see. In the ROM, I've got the screen startup code, which should be easy enough to pull out and reuse. So yes, I will report back and you'll see how I got on. I have made a ton of progress, including deciphering how most of the graphics system works, and to prove it, I've written a tool that pulls all the sprites out of the ROM and decodes them, and you're looking at them here. All 4,000 odd sprites for all the games in the ROM. This graphics data occupies most of the space in the ROM. Not all of them decode, so these are all garbage. I think that these are actually sound or music files, but I haven't figured out the format of them yet. The way the system works is quite interesting. I was right earlier. This thing is event-driven, and the big main loop is in the ROM. Every tick, it calls this routine 74, which is the main entry point for all the ROM code. There's a reference to this in the ROM header. This then calls various things here, and then one of the routines, I forget which one offhand, I think this one, calls out to whichever game is currently running. So I believe this over here, starting with this one, is a game. You can see the call graph. This then runs one tick, and then it returns back to here, back to 74, and then back to the ROM. Graphics are handled via a display list. The game here doesn't actually handle sprite data itself, it just records in data structures in RAM what gets drawn when. Then, when we go back to the ROM code, the display list then gets evaluated one scan line at a time, because of course this thing doesn't have enough RAM to hold a complete frame buffer, and each scan line is then written out to the screen. This all happens from inside the ROM, because inside the main event loop, there is no application code running, which means the code buffer from hex 300 up is unused. So it can use all that for various scanline buffers for doing the rendering. The actual sprite data is streamed from Flash during the rendering process. So for each scanline, the renderer will keep track of which row of which sprite needs to go on that scanline. It will read the data, composite everything together before drawing it all to the screen. And this happens every scanline. Luckily, the Flash system is really fast, and that Flash doesn't wear out when you read it, because this thing is doing a lot of Flash reads. Alongside the decoder, I've also written a sprite encoder, which is what you're looking at here. Internally, the system uses 8-bit per pixel graphics via a palette. What this program does is it figures out the closest color for each pixel of the source image. It then converts that to a palette index. It then RLE encodes it and writes it out as a binary file. Sprites support transparency, but interestingly, the byte value used for the transparent color is FF, which is also the color in the palette for white, so this thing can't actually draw sprites with white in them. Alongside all these tools, I've put together a build system which allows you to construct ROMs. So here is the Python description of a sample ROM. You tell it the various code chunks you want. So a lot of this is boilerplate. All this init screen stuff and rewrite and init are all pulled directly from the stock ROM. The build system takes these and also a set of sprite resources, which are simple ping files, and it will then build it all together construct the appropriate ROM header with all the appropriate stuff in it. I found actually quite a lot of stuff. In the ROM header, there is a reference to the table of the resources. There is also a reference to a font. This thing has some simple text drawing routines in the mask ROM, except they're not very useful because they use enormous quantities of RAM, so it's actually easier to draw your text using simple sprites instead. And then that's all bundled together into a simple build system, well, a rather complex build system, which will compile everything and produce an image. So here is my demo program. This replaces that routine at 7ED, so the operating system calls this once every tick. What we do first is we clear the display list. I'm using a routine here that will clear the display list and then add a single sprite all in one go because we want to initialize the screen to contain some stuff. Here we are computing the resource ID of the sprite we want to draw. Resource IDs are indexes into that resource table. The build system generates these symbolic constants for us. Every tick, we advance the background to the next frame. Then I set up to read the buttons, which involves fiddling with the GPIOs. I was right in that addresses 0, 1, and 2 are GPIOs. I also found the GPIO direction registers. Getting at the buttons is actually a little bit complicated, so I think that there are multiple peripherals attached to the GPIOs. Once that's done, I read the 2 GPIO registers that happen to represent the buttons and write them out as text. Writing them out as text involves drawing more sprites. We compute the resource ID of a digit and then call sysdrawSprite, which adds it to the display list. So we end up with a display list with 5 items on it, the background sprite and 4 digits. So all I need to do now is to burn that ROM image onto the chip. Stick the chip in the socket, apply power, and there you go. So given that all the rendering is happening in software, I think that's pretty good. If I push the buttons on the controls, you can see the numbers changing. I hope that's actually showing up on the camera. Filming these screens is notoriously hard, but take my word for it, they are actually changing. The only slight gotcha is the reset button is actually hardwired to reset, and as a result can't be intercepted in software. And before anyone complains, yes, I did get Bad Apple working on it, but there are too many frames and my command lines got too long, so I'm using this instead. So there you have it, my new 6502-based games console running homebrew code. There's plenty more to investigate. I found some of the sound code, but haven't actually figured out how any of it works. I think this thing has 3 channels of FM synthesis music. It may also have another channel for PCM audio, I don't know. Figuring that out, and particularly figuring out the format of the data in Flash, will be a little exciting because these things are notoriously impenetrable. Graphics data, by contrast, is pretty straightforward. It all has to boil down to a big grid of pixels. Audio data, particularly if the audio codec is in silicon, which it might be on this, is kinda different. I've deciphered about half the system calls, although there are still things like flags I don't know about. And there are some other things that need investigation. For example, what does this mysterious 8-way footprint do? I don't think it's an SPI flash chip. There doesn't actually seem to be any activity on it, so it's not wired up in parallel to this flash chip. Another really interesting thing is the video interface. The way you access the screen is really weird. You write to 2 addresses in upper memory, hex C1000 and hex 8000. This is completely unlike anything else on the system. This makes me wonder whether this thing might actually have an external bus interface exposed here. If so, then they've simply wired the screen up to the data lines, and one address line, the difference between the 8000 and the C1000, is wired to the command select line on the screen. That's interesting, because if you took the screen off, you might be able to hook up an actual RAM chip, the that will become memory mapped? I don't know, but that is definitely worth looking into. Another interesting thing is that the flash chip gets its power rail from the blob. It's not wired directly up to the power supply, which means it may only be powered on after the blob's complete startup. This would be great because it might be possible to program the flash chip without actually having to remove it from the board using one of these things that they clip onto the flash chip here. However, I can't do that here because my soldering has screwed up the terminals and this doesn't connect very firmly. But that would make this a whole lot easier to hack. Like, if it's just a matter of removing the PCB and plugging one of these things in, that's a completely different matter than having to desolder it and wire up stuff and put it onto a prototype board and so on. It would also be really interesting to know, well, firstly, who actually made this chip? But secondly, is this actually in current production or is this new old stock? These things look pretty new, but of course they could have been in a box on a warehouse shelf forever. There don't seem to be any markings on the PCB that mean much. There are a few numbers and there may be a manufacturer date code in there, but who knows? If it turns out that this thing is still in current production, and if there are other similar game devices or toys that use them, then that will be a source of brand new, mass-produced, current 6502-based computers that could potentially be played with. Anyway, I am going to finish here. I've got a ton of stuff to write up and post to GitHub. See the video description for the links to the actual SDK. One of the reasons I picked this animation over Bad Apple is that this is short enough to check in. So you should be able to just compile it and flash it and you'll get this. I hope other people have found that this discovery of a largely unknown 6502-based system as interesting as I do. Anyway, I'm going to leave it here. As always, I hope you enjoyed this video. Please let me know what you think in the comments, and I will see you for the next video.